Hello students, let's have a look at this example here. Projectile is launched from the top of this cliff here, and it's given a horizontal velocity of 15 meter per second. Now the new thing in this example is that a strong wind is flowing towards the left, and it causes an acceleration, a horizontal acceleration of 5 meter per second square. So in this problem, our projectile has both horizontal as well as vertical acceleration. The vertical motion of projectile, it is given, is not affected by this strong wind. The acceleration due to gravity we can take as it is 10 meter per second square. So vertical acceleration 10 meter per second square downwards, and horizontal acceleration towards left 5 meters per second square. Now in this and what we have to find is the position where the particle lands. Okay. So in this new scenario, we can't expect the results that we have derived for our ordinary projectile to hold as it is. We must think afresh how to change those results which we have got. Now as far as y direction is concerned, there is no change, because the problem says that the wind is not affecting the horizontal motion of projectile. We can write the y coordinate as it is. We are taking our usual coordinate system, y as upwards, so we can write y as ut plus half at square, uyt plus half minus half gt square. Now uy is 0 because the particle is launched horizontally. So the first term becomes 0 minus half gt square. Now the value of y when the particle hits this ground here will be minus 20, because it is 20 downwards. So minus 20 equal to minus half g is 10 into t square. This gives us t equal to 2 seconds. Okay, so now we know that the particle is hitting this point at t equal to 2 seconds. So we have to find the x coordinate. Now the x coordinate result u cos theta into t, that will not apply here, because there is some acceleration. Now because it is a constant acceleration, you can still use your second equation of motion in x direction, and we can say that x is equal to ux is simply equal to u, so it is ut. Acceleration is in the negative x direction, so minus half at square. So the second equation of motion is used here, and there is this additional term because of this horizontal acceleration. So we just have to put the values. U is 15, t we have calculated 2, minus half a is 5 and 2 squared. So this becomes 30 minus 10. This is 30 minus 10 equal to 20 meter. So the projectile will land at a horizontal distance of 20 from this corner here. Now we can add some more parts to this problem. Suppose we are asked what is the velocity of the particle with what velocity the particle hits the ground. So we need x and y components. Y component we can get simply Vy as minus gt, because Uy is 0. So this Vy is very simple, minus 10 times t is 2, so it is minus 20 meter per second square. After 2 seconds, motion freely falling from rest, after 2 seconds it should be 20 downwards, 20 meter per second. And about the x component of velocity, we have to use first equation of motion. u is 15, so 15 minus 80 minus 5 into t is 2. I have used Vx is equal to ux plus axt. A is minus 5, ux is 15. So I am getting this to be 15 minus 10 equal to 5 meter per second. So that is the horizontal component of its velocity. That means the particle, when it is hitting, we are getting a positive value of Vx. That means when the particle hits the ground, it is still moving in this direction. The trajectory that I have shown initially, that I have drawn, may not exactly be correct. In fact, because it is still moving in the horizontal direction, the path should be like somewhat like this, so that at this point the tangent drawn to the trajectory should point in this direction and not in this direction. So the path of the projectile should be somewhat like this and not coming back as I had shown earlier. Okay, so this is how the result for x and Vx have to be modified if you have some acceleration in x direction. Let us discuss the case of projectile launched on an inclined plane. Maybe this is some slope of a hill. So the inclined plane is making an angle alpha with the horizontal direction, and our projectile is launched at an angle beta above the incline. So the total angle that the projectile is making with horizontal becomes alpha plus beta. Now in this situation, projectile, after being launched, it hits the ground somewhere here, and we may have to find after what time it strikes the ground. If it is we launched at t equal to 0, so the time of flight, and maybe the range along the inclined plane, at what distance from the starting point it hits the incline. So how to do this type of questions? What we do is that we take a new coordinate system. In order to solve these problems of projectile on an inclined plane, we take our x-axis, let me call this capital X-axis, along the incline, and the capital Y-axis normal to the incline. So I have turned my axis. Rather than taking horizontal vertical, I am taking the x-axis along incline and y-axis perpendicular to the incline. This change has both advantages as well as disadvantages, but the advantages are stronger in most of the cases, in most of the problems. So what is the disadvantage? See, disadvantage of this system, this coordinate system, is that you will have to resolve G. We know the direction of G is vertically downwards. Now it is not matching with the direction of y-axis because our y-axis is not vertical. So we will have to resolve G. We have to find x and y, both components. Here this angle is alpha, so the remaining angle is your pi by 2 minus alpha. This angle again becomes alpha. So the y component of acceleration, a capital Y, is negative g cos alpha. Negative because our y direction is that one and it is against this. And ax, there is some x component of acceleration also, ax, and this is also negative because the projectile, our positive x direction is towards the right, and this is leftward, so it is minus g, and this will be sine alpha. So the disadvantage of this coordinate system was that we had to resolve g. And now let us write the xy coordinates and xy component. We can write x and y components of velocity using the first equation of motion in x direction and y direction, and we can write the coordinates x coordinate and y coordinate using the second equation of motion. Now if we have to find the time of flight, that means the moment particle hits this inclined plane, the advantage of this coordinate system is that we can simply say that this point, we can see that this point is on the x-axis, so the y coordinate here is 0, capital Y coordinate here is 0. Had we taken our horizontal vertical coordinate systems, the usual ones x and y, तो इस केस में हम ये नहीं कह सकते कि जो y कोऑर्डिनेट है वो यहाँ पे 0 होगा, बिकॉज इस x एक्सेस के ये काफ़ी ऊपर आ रहा है. लेकिन जो हमारा नया कोऑर्डिनेट सिस्टम है वो कन्वीनियंट है, उसमें ये वाला पॉइंट हम कैपिटल Y इक्वल टू 0 कह सकते हैं. नाउ व्हाट इज द रिजल्ट फॉर capital Y coordinate? We can apply second equation of motion in y direction. So uyt plus ayt square. What is uy? See, y component of velocity, the initial velocity is making an angle beta with the x-axis. So with the y-axis the angle is 90 minus beta. We can say it is u sine beta. So this is uy multiplied by t and plus half acceleration in y direction minus g cos alpha t square. So this is the y coordinate, and in order to find this point we will put this equal to 0. We can say that at t equal to capital T, this y is 0. So we get 0 is equal to u sine beta capital T minus half g cos alpha capital T squared. So one of the t is cancelled. We know it is not 0. So capital T is equal to 2u sine beta divided by g cos alpha. So this is the expression for time of flight. You can verify this result. You can check this result for a special case of alpha equal to 0. Because alpha equal to 0, if you make alpha equal to 0, the inclined plane becomes horizontal, and the formula for that case, this cos alpha is 1, and you get 2u sine beta by g, which indeed was the result for time of flight in our usual case of projectile on a level ground. Okay, so the second part will be to find the range along the inclined plane of this projectile. Range we know is the x coordinate of this point. So we need the formula for x coordinate of x coordinate. Okay. So the x coordinate we can write as, again we will apply the second equation of motion, this time along the x direction. The x component of initial velocity is u cos beta. So u cos beta multiplied by t and plus half ax is g sine alpha, negative g sine alpha times t square. So this is the general expression for x coordinate. Now if we have to find range, we can say that at t equal to capital T, this time of flight, the x coordinate becomes equal to the range. So we put these two here. So R equals to U cos beta, and capital T you can see is this. So it is 2U sin beta upon G cos alpha minus half G sin alpha times T squared. So capital T squared means square of this. So this will be 2U sin beta upon G cos alpha whole square. Okay, so we will simplify this. Let me write it here. R equals to, now we can take some things common here. 2U square by G, and 4 upon 2 again 2U square by G square, 1G will be cancelled. So 2U square by G I can take common. So twice of U square by G, this I have taken common, and from denominator I am taking cos alpha here, I will take cos square alpha as common. Let's see what is left here. So cos square alpha I have taken common. So here I have cos beta. I can take one sin beta also common. Here I have sin beta, here I have sin square beta. So I am taking sin beta also common. Now what we are left with? Cos beta, and I had taken one extra cos alpha in the denominator common. So there will be a cos alpha here. I get cos beta cos alpha. Let me create some space. Minus sin alpha and one sin beta, because the other one we have taken common. So sin alpha sin beta. Now this you must be knowing is a formula of trigonometry. We can write this as cos of alpha plus beta. So the result for range becomes 2U square sin beta cos of alpha plus beta divided by G cos square alpha. So this is the formula for range along an inclined plane. Now again we should check this result for the case that is known to us, the case of alpha equal to 0. If I put alpha equal to 0, this cos square alpha will simply become 1, and here this cos alpha becomes 1. So this will be twice of sin beta cos beta, 2U square sin beta cos beta by G, which indeed we know is the formula for range. So it is not contradicting our earlier knowledge. We can accept this result for range. This is for time of flight. Then you may be interested in one more thing. What is the maximum distance of this projectile from this inclined plane, or the maximum height above the inclined plane? So maximum distance from the inclined plane at this point, when its distance from inclined plane is maximum, what can we say about its velocity? The velocity, we can say, will not have a y component. It will be parallel to the inclined plane. It will only have x component. See, as long as the velocity of projectile has a upward y component, it will keep on going away from the incline. And after this point where the y component is 0, the y component of velocity becomes negative, so it is again coming closer to the inclined plane. So at this moment we can be sure that it will only have x component of velocity, that is capital X component of velocity along the incline. Alright, so in order to get this point or the time here, what we can do is we can put Vy or the y component of velocity to be 0. Now what is Vy? Vy again I can write using the first equation of motion. V is equal to u plus et. So uy we know is how much it is, u sine beta. So u sine beta minus, or you can say plus ayt. If the value of ay itself is negative, so it is minus g cos alpha into t. T is the time. T is a general time. This is a general result for y component of velocity. Now at this point, I will put Vy equal to 0. Here at this point I have Vy equal to 0. So if I put Vy equal to 0, I can get the time as u sine beta upon g cos alpha. And again you can check that this time is half of the time of flight. The same result we got in case of projectile on an inclined plane. At the maximum height, the time was half of the total time of flight. So that thing is same here also. Now if I have to find the maximum height, what I will do, what will be the next step? I will put the value of t back in the expression for y coordinate. At this value of t, the value of y coordinate is equal to the maximum height. So what does this give me about maximum height? I will write it here. Capital H maximum height equal to u sine beta into t. So it is u sine beta multiplied by t is your u sine beta by g cos alpha, and minus half g cos alpha into t square, cos alpha multiplied by this t squared. So it is u sine beta by g cos alpha squared, and I can write this as, in fact this is the same thing, u square by g, and u square by g is coming here also, and sine square beta here and cos beta, cos alpha in denominator. So this is basically 1, and this second term is just the half of the first one. So I can write this as u square sine square beta by 2g cos alpha. U square sine square beta by 2g cos. It will be half of this one, because this term which we are subtracting is exactly half of this. So this is the result for maximum distance of the projectile from this inclined plane. Some of you may argue that why are we changing the coordinate system? Can this problem be not solved using our usual horizontal vertical coordinate system? See, it can be done. Problem can be solved using this coordinate system also. But the solution or the thinking part may be a little complicated. So for example, if you want to find the time of flight, let me just do the first part of it using our horizontal vertical coordinate system. The problem that we will encounter, we can easily write x and y coordinate that we have already done in our horizontal vertical coordinate system. But at this point, how do we know what is the relation? We will have to find a relation, because y is not 0. So we will have to find a relation between x and y coordinates so that we can find the time. So can you see what is the relation between this y coordinate, the vertical, and the horizontal displacements of this point? If you look at this triangle, this is a right angle triangle, you can say that the small y coordinate or the vertical coordinate is equal to x coordinate into tan alpha. So y coordinate, in the usual way, we write this as, now again I will have to take the angle from horizontal. So theta that we use in our usual horizontal vertical coordinate system will be alpha plus beta here. So you will have to write y as u sine of alpha plus beta t minus half gt square. This is u sine theta t minus half gt square. Theta is alpha plus beta. So that was our y coordinate, the usual vertical coordinate, small y I am using for it. And the x similarly can be written as u cos of alpha plus beta multiplied by t, because there is no horizontal acceleration. Okay, and you can find t by putting this y equal to x times tan alpha. Y is equal to x tan alpha. Using this, it is possible to find the time of flight. You may initially get a slightly different expression, but after using some trigonometry and all, you will get the same result for time of flight. But as you can see, this choice of coordinate system, that capital X along the incline and y normal to the incline, saves you a lot of trouble in such problems, so it is preferred. Suppose we want to find the angle of projection of the projectile in order to maximize the range along inclined plane. So we have the expression for range here. Now here u, g and alpha, these are constants. We have a given fixed inclined plane and we are launching the projectile at a fixed speed u. What we can change is the direction of projection. That means angle beta can be varied. So the question is that for what value of beta will the range be maximum? Now we can do this using the concept of maxima minima. If you want to apply concept of maxima minima, you will have to apply product rule in this part. Sine beta into cos of alpha plus beta. The rest of it is a constant. Okay. So you can do this using maxima minima. But let me do this using a trigonometric formula. The formula that I will be using here is the formula of trigonometry: 2 sine A cos B is equal to sine of A plus B plus sine of A minus B. So this is a standard result of trigonometry. We apply it here. So the range becomes u square by g cos square alpha. This part I am keeping as it is. Now twice of sine beta cos alpha plus beta, I will use this result here to transform it. A here is beta and B is alpha plus beta. So it becomes sine of A plus B will mean alpha plus 2 beta. And A minus B is beta minus alpha minus beta. So it becomes sine of minus alpha. Okay. Now, the advantage of changing this from product to sum is that in this expression our variable beta is seen only at one place. This beta is appearing only here, it's nowhere else. So it's very easy to maximize this. The term containing beta will, what is the maximum value of this term? Sine of anything, maximum value is 1. So our range becomes u square by g cos square alpha times 1 minus sine alpha. Sine of minus alpha is minus sine alpha. So this is what? This is R max, the maximum range along inclined plane. And for what angle will this be maximum? I am putting this sine of alpha plus 2 beta as 1. That means alpha plus 2 beta, this will be for alpha plus 2 beta equal to pi by 2. That means the value of beta is pi by 2 minus alpha upon 2, or you can say pi by 4 minus alpha by 2. So at this angle, if the projectile is fired from the inclined plane, we get maximum range, and the maximum range is equal to this value. Again, you can verify this results for our special case of alpha equal to 0. For alpha equal to 0, we know that the range is maximum for an angle pi by 4. So if you put alpha equal to 0, you are getting beta equal to pi by 4. That is all right. And what is the maximum range? If I put alpha equal to 0 here, it becomes u square by g, which was indeed the expression for maximum range in case of projectile on a horizontal plane. So this is all right. Now if you notice, what is this angle? Pi by 2 minus alpha. See, pi by 2 minus alpha, if I measure it from the inclined plane, it is this angle. That means angle made by the inclined plane with the vertical. This angle is pi by 2 minus alpha. So beta is half of it. That means if beta bisects this angle between inclined plane and vertical, we are going to get the maximum range. In case of the projectile on horizontal plane, we got maximum range when the angle between horizontal and vertical was being bisected, or at theta equal to 45. Here, the angle between inclined plane and vertical, that is to be bisected for getting this maximum range. Let's take this example. Here, the projectile is fired horizontally down an incline. All right. And we have to find after what time it hits the inclined plane. Initial velocity u is given. The angle of incline is alpha. So this angle will also be alpha. Now, which coordinate system to use? Horizontal, vertical, or along and perpendicular to incline? Now, this is a question which you can solve by any of the coordinate systems. So let's do it using both one by one, and then we will compare the solutions. First, you can try this. Pause the video and try it. Okay, so let me first do it using our new coordinate system, capital X, capital Y. So in this code, if you are using this coordinate system, we have to resolve G, which is vertically downwards. So now if this angle is alpha, we know this is pi by 2 minus alpha. So this angle is again alpha. So the y component of acceleration, AY will be minus G cos alpha. And now we can get the time of flight by putting capital Y equal to 0, because the x-axis is along this incline, and any point on the x-axis the y coordinate is 0. So we will put capital Y equal to 0. Uh, all right. So expression for capital I we can write using the second equation of motion. So the y component of velocity, as you can see, will be this component here will be what? U sine y, u sine alpha. So u sine alpha t minus half g cos alpha t square, and we are putting it equal to 0. So t of course is not 0, so this is cancelled and we get t is equal to 2 u sine alpha upon g cos alpha, or you can say 2u by g tan alpha. Now let's do this using our old coordinate system, horizontal, vertical, small x along horizontal, small y along vertical. Now the advantage of this system is you don't have to resolve g, so you can simply write this distance, the distance by which the particle has gone below vertical. How much can we write this? See, knowing the fact that the initial vertical component of velocity is u small y is 0, we can write this as just half gt square, isn't it? Half g capital T squared, because the vertical component of initial velocity is 0. So in time t it will fall by this distance. And how much horizontal distance does it travel? In horizontal direction we know the acceleration is 0, because acceleration due to gravity is vertical. So it is just u into t. So now what is the relation between this ut and this half gt square? Can you see any relation? If you look at this right angle triangle, you can see that this half gt square upon ut, this divided by this, is tan of alpha. So we can say tan alpha equal to half gt square divided by ut. So one of the t cancels and we can get t equal to 2u by g tan alpha. The same result as we got using our capital X, capital Y coordinate system. So I took this example to demonstrate that the problem can be solved using any of the coordinate systems. The method in one coordinate system may be different or difficult as compared to the other one, but the problem can be solved from any of the coordinate systems. Alright, so the trick while solving these questions is to think a step ahead. If you can think a step ahead, depending on what is given in the question and what has been asked in the question, you can choose the coordinate system which is more efficient for you for solving that particular problem. Let me add one more part to it. Suppose I want to also find the range along the incline, this distance. Now, how to get this part? Now, if I am using the old coordinate system, horizontal vertical coordinate system, in that case, what I will have to do is that knowing the x coordinate, using trigonometry, I can get this result. What will be the x coordinate when it hits the incline? It is u into t. So this here, let me write this as x naught. So this x naught will be capital T multiplied by u. So it becomes 2u square by g tan alpha. And I can get r using this right angle triangle, I can write r as x naught sec alpha, isn't it? X naught is the base, this is hypotenuse. So I can write r as x naught sec alpha. By putting the value of x naught here, I can get the expression for range. And if I have to use the new coordinate system, I will find the value of capital X at this point. So what is the value of capital X at this point? I will have to write the expression for x coordinate using again the second equation of motion ut plus half at square. The x coordinate here can be written as the x component of velocity in this direction u cos alpha. So u cos alpha t, and the x component of acceleration, if you are throwing the projectile down the incline, is positive, isn't it? The g is in this direction, so this component is g sine alpha. So plus half g sine alpha times t squared. So you just have to put the value of t in this expression to get the range along the incline. So we have compared the two coordinate system, how the two coordinate system work in this example.